Good afternoon. So today we will read application of integrals. How we use integrals to solve real life problems. Like we use integrals to find area under a curve. Okay? We already relate definite integral with area function. Okay? So in this chapter we have studied in the previous chapter we already learned about definite integral as limit of sum and how to evaluate definite integral using fundamental theorem of calculus. Okay, so now we consider the easy and intuitive way intuitive way of finding the area bounded by the curve y equal to fx, x-axis, and the ordinate x is equal to a and x is equal to b. So in the chapter of definite integral, we already know how we can relate integrals with area function. When we calculate definite integral, it is nothing but a area of the curve y equal to fx, which is bounded by the x-axis, ordinate x is equal to a and x is equal to b. And we can find definite integral by fundamental theorem of calculus. So at first we calculate antiderivative, and by according to fundamental theorem of calculus, the value of definite integral is the value of antiderivative at a upper limit minus value of antiderivative at lower limit. Okay. For example, there is a graph. Uh, so there is a curve y equal to fx, and we can find the area bounded by the curve y equal to fx and the line x is equal to a, that is sp, and the line qr, that is x equal to b, and x axis, that is pq. So by using definite integral, we can find the area p q r s p. Okay. So we can think of area under the curve as composed of large number of very thin vertical strips. As in figure, we can see dx and y, these are strips. So all the curve or this area can be considered as a composed of large number of very thin vertical strips. So at first we find the area of this vertical strip, and then by using the integrals we find the area of the entire region. Consider an arbitrary strip of height y and width dx. Then dA, area of the elementary strip, is equal to y into dx, where y is equal to fx. This area is called the elementary area, which is located at an arbitrary position within the region which is specified by some value of x between a and b. So at first we calculate the area of the elementary strip, and for an elementary strip, height of the elementary strip is y and its width is dx. So area of elementary strip is y into dx, where y is a function of x. Okay. We can think of total area A of the region between x axis, ordinate x equal to a, x equal to b, and the curve y equal to fx as the result of adding up the elementary areas of the of thin strips across the region p q r s p. So we can write it as area of the region PQRSP. From the last figure, the region area of region PQRSP is given by when we integrate from A to B. Here A is lower limit, the line x is equal to A, and the line x equal to B. So we integrate from A to B dA. What is dA? dA is the area of the elementary strip. So when we integrate that elementary strip from A to B, from the line x is equal to A to the x equal to b, we get the area of the entire region. So what is the value of dA? Area of the elementary region is y into dx, where y is the height of the elementary strip into dx. Dx is the width of the elementary strip, and dx vary from a to b. So it can written as different integral from a to b y into dx is equal to, and now we write y as a function of x. So y is equal to fx. So y become fx. So we get different integral from a to b fx dx. So when we find this definite integral from a to b fx dx, that is equal to the area of the region PQRSP. Okay. The area of the region bounded by the curve x is equal to zy, y-axis, and the line y equal to c, y equal to d is given by a is equal to definite integral from c to d x dy is equal to c to d gy dy. So in the previous figure 8.1, we taken the strip that is parallel to y-axis, vertical strip. And this figure 8.2, we taken the strip, the elementary strip is parallel to x-axis. And here the height, the length of the strip is x, and the width of the strip is dy. But in the previous figure 8.1, the height of the elementary strip is y, and width of the elementary strip is dx. So on that figure, we integrate from x equal to a to x equal to b and calculate definite integral fx dx from a to b to find the area. Okay, but here in this figure we integrate for y. Here the width of the strip is dy, so integrate from y is equal to c to y equal to d. Okay, so to calculate area in the definite integral, we at first break the whole area into thin strips. Okay, and calculate area of the strip, and by integrating we find the area of the whole region. So to calculate the area of the curve x equal to zy and the lines y equal to c and y equal to d and the y axis, so bounded by these lines, the area is calculated as definite integral from y equal to c line to y equal to d. So here lower limit is c and upper limit is d. So we calculate definite integral from c to d into x dy. Here x dy is, what is x dy? So as we can see, the area of the elementary strip, as length is x and width is dy. So area of this elementary strip is x dy. So when we integrate this elementary strip x dy from the limit c to d, we get area for the entire region. Okay, and when we convert x in right in the form of variable y, in place of x we substitute gy, so we get definite integral from c to d gy dy. So to calculate area of a curve under the curve bounded by the line x equal to a, x equal to b, or y equal to c, y equal to d, we can use this both. We can use in both way. We can take as elementary strip parallel to y axis, or we can take elementary strip parallel to x axis. But when we take parallel to y axis, it means a vertical strip. Then we integrate from in the limit of x axis. And when we take elementary strip parallel horizontal strip, then we integrate for a limit upper limit y. For y we take upper limit lower limit as y is equal to c and then d. Okay, clear? So here we consider horizontal strip as shown in figure 8.2. So there are two methods. We can take vertical strip and horizontal strip. When we take vertical strip, we take limit for x, and when we take horizontal strip, we take limit for y. Okay. So in this figure, if the position of the curve under consideration is below the x-axis, here the curve is below the x-axis, then since fx is less than 0, fx is negative from x is equal to a to x is equal to b. Just carefully observe in the figure. We take the curve y equal to fx, that is lie below the x-axis, and since fx is negative, fx is less than 0, and we want to find the area of the region bounded by the line x is equal to a and the curve y equal to fx and the line x is equal to b and your x-axis. The blue color region, we want to find the area of this blue color region. So it is bounded by the line x equal to a, the curve y equal to fx, and x equal to b, and the horizontal axis x-axis. Okay. But in this region, fx is less than 0. The area bounded by the curve x-axis and the ordinate x equal to a, x equal to b come out to be negative. Why? Because fx is less than 0. But it is only the numerical value of the area which is taken into consideration. Thus, if area is negative, we take its absolute value. Area is always positive. So, if the curve lie below the x-axis, we take its absolute value to find the area of that region. Okay. So, now see the figure 8.4. Generally, it may happen that some portion of the curve is above x-axis and some is below the x-axis. Okay. So, in this figure, the first portion, the area A1 is lie below the x-axis and some portion, the area A2 lie above the x-axis. So in this case, how we calculate area of this curve? So we have to calculate area A1 and also A2. So as A1 is less than 0 and A2 is greater than 0, therefore the area A bounded by the curve y is equal to fx, x-axis, and the ordinate x is equal to a and x is equal to b is given by area is equal to mod absolute value of area A1 plus A2. So when the curve in such a way that some portion of the curve is lie above the x-axis and some portion lie below the x-axis. So to calculate in area of the entire region, we calculate area in two portions. First, we calculate area below the x-axis and area above the x-axis. So the area which is calculated below the x-axis, we take it as we take in absolute value plus the area which we calculated above the x-axis. Okay. So the example one is find the area enclosed by the circle x square plus y square is equal to a square. So we have at first we have to draw graph for this curve x square plus y square is equal to a square, and this curve is circle. So at first draw the circle of x square plus y square is equal to a square, and then find the limit from where the circle range, and then using the definite integral find the area of the circle. So try this question. So to solve this question, to find the area enclosed by the circle x square plus y square is equal to a square, at first we have an idea how to draw this graph. Okay, so the equation x square plus y square is equal to a square represent its origin is at 0 0, and a is the radius, as equation of circle is x minus h whole square plus y minus k whole square is equal to a square, where h and k is your point of center and a is radius. So here in this equation, as x square, that is x minus 0 whole square plus y minus 0 whole square is equal to a square. So 0 0 is the origin and a is the radius. So now we have information that the circle whose center is at origin, and we have to draw a circle with radius a. So we get figure 8.5. Okay. Now, as radius is a, so coordinate of point A is a0 and coordinate of point B is 0 comma a. Okay. So to calculate the area of this entire enclosed circle, the first we can see that some region is below the x-axis and some are above the x-axis. But the whole area enclosed by the given circle is equal to 4 into area of the region AOBA, bounded by the curve x-axis and the ordinate x equal to a and x is equal to a. Okay. So due to symmetry nature, if we calculate the area AOBA and when we multiply with 4, we get the entire area of the circle. Okay. So now we have to calculate area of the region AOBA, and this area is enclosed by the curve x-axis, the horizontal axis, and the ordinates x is equal to 0. X equal to 0 means the line, vertical line, that y-axis, and x is equal to a, the x is equal to a line when we draw a line at the point a, the vertical line. So we have to calculate area in this region and the curve y equal to fx, and the curve is circle. Okay. As the circle is symmetrical about both x-axis and y-axis, so we get area is equal to 4 into definite integral from 0 to a y dx. So here we take vertical strip, and when we take vertical strip, we write the limit of x. So x ranging from x varies from 0 to a. The first value at the is x equal to 0 line and the last is x equal to a line. The curve is bounded between these both vertical lines. So the limit is 0 to a, and the area of this thin vertical strip is y into dx. So to calculate the area of AOBA, we just find the definite integral value from 0 to a y dx and then multiply it with 4 to find the area of the entire region. Now, since x square plus y square is equal to a square, and to find the value of definite integral from 0 to a y dx, at first we have to write y in the variable in the form of x. So in place of y, we can write y is equal to plus minus root under a square minus x is x square. And since the region AOBA is lies in the first quadrant, y is taken as positive. So we take the value y is equal to root under a square minus x square. So my area is become 4 into def integral from 0 to a root under a square minus x square dx. Okay. So we get the whole area enclosed by the given circle. So as we know that when we integrate root under a square minus x square, we get x by 2 root under a square minus x square plus a square by 2 sine inverse x by a plus constant of integration. So by using this formula, we can find the value of def integral from 0 to a root under a square minus x square. So area is 4 into x by 2 root under a square minus x square plus a square by 2 sine inverse x by a. And as you can see here, we doesn't take the constant of integration because we have to find the value of antiderivative, not indefinite integral. And what is the difference between antiderivative and indefinite integral? The only difference is in the indefinite integral there is present a constant of integration. So now to find the value of this area, we apply the second fundamental theorem of integral calculus. So at first we put the upper limit value at the value that antiderivative minus lower limit value is 0, so we get 0. So we get 4 a by 2 into 0 plus a square by 2 sine inverse 1, and the value for sine inverse 1 is pi by 2, so we get 4 into a square by 2 into pi by 2. So when we simplify, we get pi a square. So area of the circle is pi a square, and by the geometry we already know the area of the circle is pi r square, where r is the radius. So the first task to calculate area of any curve is to construct a graph for that curve, and then we have to draw either a vertical strip and horizontal strip, and according to vertical and horizontal strip we find the limit from where to where we have to find the value of definite integral, and then just apply the fundamental theorem of integral calculus to calculate the value of definite integral. You get the area of the curve. So in the first way we take the vertical strip, but we can also use horizontal strip to find the area of the this circle. So we take the horizontal strip which is parallel to x axis. We take a strip with length x and width dy. So area of this strip is x dy. And when we take horizontal strip that is parallel to x axis, we take limit for dy y. So y varies from the first line horizontal line x axis. So y varies from 0 to a. The first line is y equal to 0, the x axis line, and the last line, the point B, is the line y equal to a. So y is varies from 0 to a. Okay. So now we have to calculate the value of definite integral of x dy from 0 to a. So considering horizontal strip as shown in figure 8.6, the whole area of the region enclosed by circle, as we know that integration of a square minus y square dx is equal to y by 2 root under a square minus y square plus a square by 2 sin inverse y by a plus c. So my area has become 4 into integration 0 to a x dy, the area of the that strip, thin strip, and that area is x into dy. Now we write x in form of y, and by using the equation of circle, we can write x as root under a square minus y square. We take positive sign because we calculate area in the first quadrant, and where x is positive, so we get 4 into integration 0 to a root under a square minus y square dy. So area is become by using the our formula 4 into y by 2 root under a square minus y square plus a square by 2 sine inverse y by a. Lower limit is 0, upper limit is a. So just apply the second fundamental theorem of integral calculus. First, in place of y, just put a. So a by 2 into a square minus a square, so it becomes 0, plus a square by 2 sine inverse a by a, that is 1, and then minus, and then now put y is equal to 0. So when we put y is equal to 0, we get 0. So when we simplify, we get 4 a square by 2 pi by 2, that is pi a square. So either we use the horizontal strip or vertical strip, we get the same answer. We use the horizontal vertical strip according to the variation limit, in which case we get the simple limit or difficult. We understand by doing post. So now you have to find the area enclosed by the ellipse. X square by a square plus y square by b square is equal to 1. So to solve this question, to find the area, at first we know how we can draw ellipse and what is a, what is b in the equation of ellipse, so that we can draw the graph of ellipse. And when we draw the graph of ellipse, we have to find which area is lie below the x-axis and which is above the x-axis, or is it there a symmetry, so that we can find the some part of the area and just multiply it with any numerical constant multiple, so that we get the area of the entire region. As in the case of circle, we just calculate in the first area of the first quadrant and multiply with 4 to get the area of the entire circle. Can we do the same in the ellipse? Is ellipse symmetry? So at first, the first task is draw the ellipse where, and then see it is symmetry or not, and after that you can draw a horizontal strip or vertical strip, and according to horizontal strip and vertical strip, you find the limit. Okay, so when we take horizontal strip, the limit is for x, and when you take so in that way, so just at first draw the ellipse and try to solve this question. When we draw the ellipse x square by a square plus y square by b square is equal to 1, we get figure 8.7. So here we can see the point a comma 0, and the point b, 0 comma b dash, 0 comma minus b, and a dash minus a comma 0. So now we have a graph, and we have to find the value of the area enclosed by this graph, the ellipse. So as you can see the symmetry nature in this graph. So when if we calculate the area of the first quadrant, so the area OABA, and just multiply it with 4, we get area of the entire region enclosed by the ellipse. Okay. So the area of the region A, B, A dash, B dash, A bounded by the ellipse. And that area is equal to 4 into area of the region AO, BA in the first quadrant bounded by the curve, and x-axis and the ordinates x is equal to A and x is equal to 0 and x is equal to A. So to calculate area in the region present in the first quadrant, we take vertical strip that is parallel to y-axis. So the height of this vertical strip is y and width is dx. You can consider the strip as rectangle, and area of the rectangle is L into B, length into breadth, and here the length is y and the width is dx. So the area of this thin vertical strip is y dx. Now to find the area of this entire AOBA, we just integrate this thin strip from the line x is equal to 0. That line is y-axis. X equal to 0 represent y-axis. So we take the line y-axis and x is equal to a. The x is equal to lane a is a line that is crossing from the point A and parallel to y-axis. Just imagine. So we calculate area from the line x equal to 0, that is y-axis, to the line x is equal to a, that is parallel and crossing from the point A. Okay, and we just integrate this thin strip, that is y dx. So we just break this region into many number of strip, and by using the integration, just integration is limit or sum of limit. So when we read sum of limit, we just understand how we calculate area of this region by using definite integral. Okay, so understand. So here the limit is x is equal to 0, dx varies from 0 to a. Okay, so as this ellipse is symmetrical about both x and y axis, so when we multiply this region with 4, we get the area enclosed by the ellipse. So area is equal to 4 into 0 to a y dx, taking vertical step. So when we take vertical step, this limit is for x. Limit is for dx. So just see the dx. If there is dx, we write for the limit of x, and if there is dy, we write limit of y. So x varies from 0 to a. Here y is an independent variable. Okay. So to find the value of definite integral, we have to write y as in x, in the form of x with variable x. By using variable of x, we have to write y so that we can integrate it. So at first, we have to write y in x. So we have an equation of curve, that is x square by a square plus y square by b square is equal to 1, gives y is equal to plus minus b by a. Just take y in one side, left hand side, and take all the thing on the right hand side. So we get y is equal to plus minus b by a root under a square minus x square. So we write y in terms of x. But as the reason AOBA lies in the first quadrant, so y is taken as positive. Clear? So we take value y is as plus b by a root under a square minus x square. So the required area is 4 into integration 0 to a b by a under square root a square minus x square dx. So when we integrate this 4 into 0 to a, when we integrate 0 to a b by a root under a square minus x square dx, we get the area of that region in the first quadrant. And due to symmetry nature, when we multiply it with 4, we get the area enclosed by the ellipse x square by a square plus y square by b square equal to 1. Now, as we know that integration from root under a square minus x square dx is equal to x by 2 root under a square minus x square plus a square by 2 sine inverse x by a plus c. That is value of indefinite integral. But to find the definite integral, we have to find the value of antiderivative. And antiderivative and indefinite integral is same. The only difference is the constant of integration. So area become 4 b by a. B by a is constant. To come out the sign of integration, so we get 4 b by a, and apply the formula, we get x by 2 root under a square minus x square plus a square by 2 sine inverse x by a. Lower limit is 0 and upper limit is a. Now we have value of antiderivative. So to calculate the value of definite integral, now we apply the second fundamental theorem of integral calculus. So what is second fundamental theorem of integral calculus? It says that the value of definite integral from a to b fx dx is equal to, if capital F x is the value of antiderivative, then the value of antiderivative at upper limit, that is fb, minus the value of antiderivative at lower limit, that is f0. So just put first upper limit, that is a, so we get a by 2 into 0 plus a square by 2 sine inverse 1 minus the value at lower limit. The value lower limit is 0, so we get 0. Okay, clear? So we get 4b by a by 2 into 0 is 0, a square by 2, and the value of sine inverse 1 is pi by 2. So when we simplify it, we get pi a b, and that is the area enclosed by the ellipse x square by a square plus y square by b square. So another way. So in the first part, we take the strip parallel to y-axis, the vertical strip. Now we can also solve this problem by taking the horizontal. So to find the area enclosed by any curve, the first problem is to draw the graph for that curve, and then see how we can, then the second problem is we have to see the curve lies below the x-axis and above the y-axis. If it is below the x-axis, we take the absolute value, and if it lie above the x-axis, we take the doesn't need to take the absolute value. Okay, but in this problem, now we take the horizontal strip that is parallel to x-axis. So the length of the strip is x and width is dy. So if we consider it as rectangle, the area of the strip is x dy. Okay, so now we have to calculate the area a b o a, and to calculate we have to find the limit, and as we take the horizontal strip, so the limit we have to take limit for y, and this area is enclosed in the region the line y is equal to 0, that is x-axis, and the line which is parallel to horizontal axis x-axis and passes through the point B, the, the horizontal line y is equal to B. So y equal to 0 and y is equal to B, the area is enclosed in this region. So the y varies from 0 to B. So to calculate the area of this blue region, we have to find the value of definite integral from 0 to B. The limit for y 0 to B and x dy. So area is equal to a is equal to 0 to B x dy. Okay. So considering horizontal strip as shown in figure 8.8, the area of the ellipse is, due to symmetry nature, just calculate the area in the first quadrant and then multiply it with 4 to get area of the entire ellipse, entire region. So 4 into, just say the limit, we take 0 to B, that is limit for dy. Why? As I already told you, we have to see the limit for dx. If there is dx, limit of x, and if there is dy, the limit of y. So y varies from 0 to b. So 0 to b x dy is equal to 4 a by b. Now we have to write x in the form of y. So by using the form equation of ellipse, x square by a square plus y square by b square equal to 1, we can get the value of x. So x is equal to a by b plus minus a by b root under b square minus y. And as we calculate area in the first quadrant, so we take the positive value, we get 4a by b definite integral from 0 to b root under b square minus y square dy. Okay. So as we know that integral of root under a square minus x square dx is equal to x by 2 root under a square minus x square plus a square by 2 sin inverse x by a plus c, that is the value of indefinite integral. So from the value of indefinite integral, we get the value of antiderivative. So get area is equal to 4a by b y by 2 root under b square minus y square plus b square by 2 sin inverse y by b. Here the upper limit is b and lower limit is 0. So now we apply second fundamental theorem of integral calculus to find the value of definite integral. So we get 4a by b. So at first put y is equal to b. So b by 2 under square root b square minus b square, that is 0, plus b square by 2 sin inverse b by b, that is 1, minus the value of this antiderivative at 0. So when we put 0, it's 0 by 2, that is 0, and b square by 2 sin 0 by b, that is sin 0, sin inverse 0, and sin inverse 0 is 0. So we get 4a by b by 2 into 0 plus b square by 2 sine inverse 1 minus 0. So when we simplify, we get 4a by b by 2 into 0, 0, b square by 2. The value of sine inverse 1 is pi by 2, that is pi ab. And hence, that is the value of area enclosed by the ellipse. So we can take horizontal strip or vertical strip, whatever, we get the same area. Okay. So by using the definite integral in this today class, we see how we can calculate area enclosed by a curve, horizontal x-axis, and the line x equal to y or x equal to b in case of vertical strip. Also, we can take horizontal strip. So when we take horizontal strip, we integrate from the y is equal to c to y is equal to d to find the area of the curve. Okay.